Okay, welcome to this next lecture where we're going to get to grips with how radiation interacts with matter. And because, of course, radio astronomers and all astronomers really are observing just the radiation that's coming in from outer space, we really need to understand how radiation and matter interact. Essentially, if we are to use the radiation that we see to infer the physical conditions in the objects in the distant universe that we were observing. So this will be a fairly sort of theoretical kind of physics heavy lecture. So those without that kind of physics background, just bear with us through this one, I think. And we'll just try and bring out, the key concepts, and we'll apply them later in the workshop as well, just so you can see how we use these concepts in radio astronomy. So I'm going to talk about, as I said, how radiation interacts. So that's going to take us to a concept of opacity, which deals with, how photons are either absorbed or scattered by matter. And then in the second half, we'll look at an equation that we can derive to show how this works, how the intensity change of radiation changes as it passes through matter, and then look at a particular solution for radio waves, which makes things a little bit easier and also brings in some other key concepts as well. So, as I said, radiation, which you can, sometimes it's better to think of it as an electromagnetic wave, other times it's better to think it as a photon, as a particle, will interact with matter, by which we usually mean in an astrophysical context, gaseous atoms, ions, or molecules. And it can do that either through absorption or scattering, which we will differentiate in a moment. And I'm going to introduce a physical property of matter called the opacity of the material. So the name comes from the idea of, some materials or media are opaque to radiation, so you can't see through them very well, and others are transparent. And it's this opacity that, describes that kind of quantity. So let's think about these two processes, absorption first. So absorption of a photon means that, the atom or ion or molecule that it is interacting with actually, fully absorbs all the energy in that photon and basically destroys the photon. So the photon no longer exists. All the energy in that photon is transferred into the atom. Let's just use the word atom for now. And it will normally excite an electron into a higher energy level when you do that. And of course, sometimes later, that same atom might de-excite and the electron will drop back down from that level and emit a new photon. But that new photon would be emitted firstly in a random direction and probably also at a different frequency altogether. So there is no memory of that initial photon at all. And these absorption processes take a variety of forms, and we can sort of classify them by the type of electronic transition that is taking place in the particle, atom, ion, or molecule that is doing the absorbing. So let's flesh that out a little bit. So again, let's just think of atoms for a moment. So atoms have, because of quantum physics, they have particular bound energy levels. So that in particular energies, distances from the nucleus where an electron can orbit, and only those. And we can talk about a particular type of transition going from one of these bound energy levels to another bound energy level. And that would be referred to as a bound-bound transition. So you're going from one bound energy level in an atom to a higher bound energy level in that atom. And the difference in energy between those two levels correspond to the energy of the photon, which is just proportional to its frequency. So these kind of interactions are what would give rise to a spectral line. Okay, so it's the difference between two energy levels that corresponds to a particular wavelength or frequency of a photon. And therefore, if you start absorbing all the photons at a particular wavelength, then you get an absorption line in your spectrum, because those photons with those particular wavelengths have been removed. Okay. If you put more energy in with your photons, higher energy photons, then you might move your electron from a bound level in the atom to completely out of the atom altogether, so that you've removed the electron from the atom. So that is the process of ionization, and in particular photoionization, because we're using photons to do the ionization, to remove the electron from the atom. And so this can be described as a bound-free transition, or as I said, it's the process of photoionization. And if you look at how this opacity would change with frequency in this case, it would look like a continuum, because almost any energy level, any wavelength of photon could in principle ionize an atom from a particular level, but it will have big steps in it. So as you go across a particular ionization threshold, an ionization potential, if you like, from one side to the other, suddenly it will be much easier to absorb your photon if you can suddenly ionize from a new level than before. Okay. So this is referred to as bound-free. Okay. And lastly, very important for radio astronomy, is this process of free-free. So this is where the electron is already not bound to an atom. It is a free electron, but it has to be in the vicinity of a positively charged particle, an ion, because here the energy of the photon will go into accelerating the electron away from the ion. And so therefore the electron is absorbed again. And here there are no particular frequencies or thresholds at all. It's just a pure continuum process. So another name for this process is the German word Bremsstrahlung, from braking radiation, because, well, that's the opposite process, where you slow an electron down, you decelerate it, and it emits. But the free absorption is another way that a photon can be absorbed by an electron, in this case a free electron, in the vicinity of an ion. Okay, so those are different types of ways in which photons can interact with matter where the photon is absorbed. And it's nice to illustrate this with a simple energy level diagram. So this is the energy level diagram of atomic hydrogen. So we have these different quantized energy levels here, and the electron could be in any one of these energy levels. So for instance, you've got an example here. The electron might be in the second energy level, and a photon with just the right amount of energy comes along to put it into the fourth level instead. And so the photon here would be absorbed, and that would be a bound transition from one bound energy level to another bound energy level. If the electron was in the ground state here, the bottom level, and a very high energy photon came along with enough energy to take the electron all the way out of the atom here into the continuum levels, into the, just outside the atom altogether, that would be an ionization process, a photoionization process, and that would be a bound-free transition. If your electron was already up here in the sort of outside the atom but nearby, it could move from here, for instance, oops, from here just a bit higher, and that would be a free transition. Okay, so that was absorption. We can also have scattering processes. So in scattering, we do not destroy the photon, we just change its direction. Okay, but again, if you're looking along a particular line of sight and an electron comes along and gets scattered out of that line of sight, then of course you no longer see it. So sometimes it's difficult to tell whether it's been absorbed or scattered. But there's a particular type of scattering which occurs out there in the universe, which is Thomson scattering. So these are free electrons, so they're a long way from any ions. And in this case, the photon is redirected, but its frequency is unchanged. It's basically like an elastic collision between the photon and the electron. And so it's illustrated here. In comes a photon, it goes off, scattered in a different direction, and the electron scatters off also in a different direction. But the wavelength here stays the same. There is a higher energy version of this, which is Compton scattering, which is an inelastic collision, and then the wavelength of the photon changes too. But these are all continuum processes. There's no particular frequency here. Okay, so that's got us starting to think about how photons interact with matter. So we'll take a little break here before we get into the mathematics of the transfer equation. So before that, let's just take a 5-minute break. And perhaps during that, you can have a little think amongst yourselves about examples of absorption and scattering processes that occur in optical light as you look up at the sky here. As optical light is traveling through the Earth's atmosphere, can you think of different examples of absorption and scattering processes that you can kind of see just by looking up in the air? Okay, we'll come back after the break.